Welcome. So this is the last video on physics. I had my fun with it, but at one point, yeah, it's more like an HBO miniseries. Um, the last one is just a side effect that basically arose, and I want to document my thoughts here. It might be wrong. Yeah, I don't know. Because yeah, you've watched my video on the atomic nucleus, then you know that I don't like the magic in modern particle physics. I mean, this is maybe it's cool for the people who do this, but it's not, in my opinion, it's not founded. But let's go. This is about the wave particle duality, which is obviously also kind of magic. Oh, it's both. Well, the problem with both is both cannot be. It's as simple as that. Both cannot be. Assume you have to pick one. Which one would you pick? Well, yeah, you can hold the video and think a little bit about it. Mm, um, I'll give you a couple of seconds. Okay, you've picked one. Well, I picked particle. The reason is very simple. Things cannot be waves. Waves are kind of a second order phenomenon. You need some kind of a medium. Well, there is no medium. Well, we will see this. So, um, now think about a, a water molecule. A water molecule, and think about an ocean. So, what's the medium the ocean is in? There is none. Take away the water molecules and you end up with nothing. A vacuum and then well, all the, but there is basically, and yet if you are on the ocean, you see a lot of waves. So is there a particle wave duality with water? No. But because water is such a strong dipole compared to other molecules, they act easily with each other, and therefore you can have waves inside water, or basically, yeah. And so I thought, well, the only thing that we need to assume is that light can interact with light. So is this so strange? Well, first of all, let's have a look at the Michelson-Morley experiment. The Michelson-Morley experiment clearly shows that light does not move in a medium. Because, yeah, there's a very easy way to calculate this. You take a river and you row upstream and then you row downstream the same distance. And then you do the same vertical to the stream. So across the river and back. And if you cover the same distance, you will see, and because there's a medium involved, the time to travel is different for upstream, downstream, and across the river and back. And because the Michelson and Morley experiment does show there is no difference, that would point to light is a particle, basically like Newton. Besides, it's actually kind of interesting. Newton and Huygens, they knew about each other. They actually discussed their theories. Huygens said, well, it's wave. Newton, he used the word corpuscle, which is basically mini particle. Um, but nobody came to the idea it's both. And later on, we had a lot of heavy things throwing into the wave, like there is Young, the famous double slit experiment. There was Brunel with his lenses. Uh, but then there's Planck, which is particle. And so, so my basic idea was, yeah, light is a particle, but it can interact with other particles, which is basically the photon would be able to interact with other photons. You can think about a lot about problems that this would make, but so what kind of interaction could this be? It's actually quite simple. Gravity. Because we know that light can bend under gravity, so it is influenced by gravity. Now, modern physics tells us light doesn't have a mass. Okay, but this is thinking different. And basically, light has speed, light has has energy. Um, so if it has energy and it has a velocity, then we can apply E equals mc square, and that means we can calculate a mass. Likewise, we can then, according to basically, yeah, we have the Planck constant, and we have frequency over c, I think it was something like this. So it's also energy, and so we can equate these two. Let me look this up. How? So okay, so we have E is equal to mc square, and therefore the mass is equal to E over c square. I take the historic one. Modern ones take the word for the W for work and energy. But so this is basically how Einstein, because that was German based and W is international based. So, and then we have, yeah, let's have a look how this, what is the energy of a photon? So let me see, energy of a photon is h over c, is h times c over lambda. Okay, so the energy is h times c over lambda. And with, yeah, so we we have a lot of possibilities to equate this, and yeah, and then we have F is G times m1 times m2 over r square, and m1 is equal to m2, so we have is equals to m square over r square. And if we want to have the distance, then we have r is equal to m square. Oh, let's actually m square divided by, let's make this big G. It looks nicer. So it's big G over F. This is R square, and therefore R is M mm, R is equal to M times square root of G over F. Okay. Did I make any mistake here? Let's see. Okay, I'm missing a G here. Yeah, so that's basically, and now we can put this in there and can get the distance depending on the force. But you can do this calculation and you see there is a force and we don't know the actual. Well, we can calculate the mass, but there's something interesting because the mass is also frequency or wavelength dependent. This would mean that different frequency would have different forces, and that would mean that the wave patterns would be different. That's what we are seeing. Higher frequencies have a different wave pattern than lower frequencies. So actually, this is not too difficult to assume. And I don't know why we need any duality here. I don't see it. There might be arguments for this. It's fine. The same is actually true for electrons. Electrons, they have clear force between them because they have a field. Yes, in this case, it's a repelling force, but it actually doesn't matter. Force is force. If you take three particles, this is completely balanced if this distance is equal to this distance. But if you start basically something like d1 minus delta 1 minus delta, and the other one is d2 plus delta. And d1 equals to d2 is equals to d, so let's remove the indices. So you have d1, and then you have force pad. You have basically everything you need for vibrations and what for waves. So yeah, that's all you need. I don't know why we need this complicated wave-particle duality. So basically, I'm with Newton. Newton said it's a particle. Okay. And there might be arguments. It is just, these were thoughts, and it's actually at the end of everything what I did. I don't really care if it is completely correct or not. If someone has a really good counter argument, I'm happy to learn. It was an honest attempt, but if you have a good argument against, yeah, you have the comments. Try a good argument against the nucleus. So my claim there is no nucleus. I've yet to see one. So physicists are basically currently playing the ostrich. Yeah, I don't want to know this. Um, there is no argument I've heard. Yeah, that's basically. So, this is my take on wave-particle duality. It's actually not needed. We just need to assume it's a particle and it can interact with other particles, and then we have everything we need. Everything fits neatly. We have wave behavior because these particles interact with each other, and we have particle behavior because they are particles. So thank you and I hope you had some fun and it actually provoked some thoughts. If you have something that makes it wrong, assuming basically going to the textbook and commenting in the textbook is different. I know that. So that's nothing new, really new. Maybe you have a good argument why um, the simplification is actually too simple, which might be true. So thank you for listening, and the next video will be about geology, or basically, so I have my thoughts about the asteroid which killed the dinosaurs. Um, I have some interesting ideas about that one. And then I will probably do some stuff about education and programming, which I really enjoy. Thank you and enjoy your day.